So this afternoon, I'm going to tell you a little bit about our work on sort of at the boundary between thinking about electronic structure and programming on quantum computers. And how can we use, for example, the emerging technology and possibilities of quantum computers to enhance our ability to solve many electron systems. So the title of my talk today is Contracted Quantum Eigensolvers for the Quantum Simulation of Many Electron Systems. And in the process of going through the talk, I'll explain what do I mean by contracted quantum eigensolver, and we'll go from there. My two co-authors, Scott Smart and Jan Nicholas Boyne, just graduated actually in April, and both going on to postdocs. Scott's going to be postdocing with Karina Reng at UCLA, and Jan Nicholas Boyne with Emily Carter at Princeton. So they're just starting some new stuff this summer, and so I'll be talking about some of their work here. So just some brief background. So molecular simulation on quantum computers. Basically, quantum computing has the potential to be a technology disruption. We've seen obviously big advances before, from things as simple as the abacus to, of course, the development of computing. Actually, quantum chemistry, interestingly, started with basically humans doing the calculations. And in fact, in the early days, when the first calculations were done, for example, on molecular hydrogen by Coolidge and James at Harvard, they actually went and hired a team of women to serve as sort of women computers to do all the calculations for the first calculations of H2. And so here's actually a picture that's kind of representative of the type of adding machines that were used to do the calculations. And of course, in the 1940s, we had the rise of the ENIAC and other computers. Here, just the size of the computer, of course, weighing 30 tons, using 200 kilowatts of electric power, contained 18,000 vacuum tubes. So kind of just remarkable how much, obviously, computing is advanced. Perhaps some of you remember the beginning of personal computing in the early 1980s. Computers like the Atari 800, pictured here, had something on the order of 16 kilobytes of memory. Of course, a fraction of what we now carry in our phone, for example. And of course, today we have laptops like the Mac and other laptops. And really, right now, we're kind of at the precipice of many exciting advances in computational science. For example, exascale computing is coming online. Here's a kind of representative picture of the Aurora supercomputer at Argonne National Laboratory that's going to be completed a little bit later this year, hopefully. And also the rise of quantum computers. So for example, here on the right, we have IBM's Quantum Experience, where we basically replace the bits of classical computers with quantum bits that can become essentially entangled between zeros and ones. So quantum computing, in many ways, is obviously in its very early days. And one of the themes that actually emerged, I think, in the early days of classical or traditional computing for quantum chemistry and electronic structure was an exploration of many different ways to try to solve different problems. And of course, that continues today with many new advances in creative approaches to thinking about how we can describe atoms and molecules and so on. And on quantum computers, in many ways, it's still early days. And so one of the earliest, one of the kind of dominant approaches today is something called the Variational Quantum Eigensolver, or VQE, for quantum computing. But it really just goes back to the Rayleigh-Ritz variational principle developed by Rayleigh and Ritz. So here we see Walter Ritz pictured here in this photograph from the early 1900s. Ritz wrote a paper in 1908 where he basically recognized that one could perform a unitary transformation of a wave function and then use the parameters in the unitary transformation to perform an energy minimization. And of course, we know that this is going to be an upper bound to the ground state energy by the variational principle. So on a quantum computer, this is the Rayleigh-Ritz variational principle is sort of given the name variational quantum eigensolver. And given some unitary transformation, one minimizes over a series of parameters theta, minimizing the energy where these unitary transformations are applied to the wave function to transform it to hopefully something close to the correct ground state wave function. And then once the wave function is generated on the quantum computer, we actually don't want to bring that wave function back to the classical computer, because then essentially the cost is exponential. So what is really done on a quantum computer is the state is prepared on the quantum computer, and then a measurement of quantum tomography is performed to calculate the components necessary to measure the energy. And sort of the natural quantity used is the two-electron reduced density matrix, whose elements then allow us to evaluate the energy of the quantum system. So the 2-RDM in some form is computed or measured from the state on the quantum computer, and that information is then brought over to the classical computer in the variational quantum eigensolver to complete the calculation. So first of all, it's a very general algorithm, and ultimately we need to actually consider what will we choose for the unitary transformation. What's the physical intuition in picking H? How large, for example, should our parameters in theta, for example, be? So we have potentially a bunch of parameters in the real or complex plane. We have to figure out what those parameters are going to be. The parameterization of the wave function might be over or under redundant. So we may not have a flexible enough Onsots, or the Onsots may actually be too complex, for example, for a given problem that we're looking at. So how do we make progress beyond variational quantum eigensolver? And so that's the theme for today's talk, is to talk about a family of different eigensolvers that we call contracted quantum eigensolvers. So the CQE, or contracted quantum eigensolvers, start with something called the contracted Schrödinger equation. So the idea of the contracted Schrödinger equation is that we take the Schrödinger equation and then we test it with all two-particle excitations, de-excitations, and transitions from the wave function. And that process of testing produces this contracted Schrödinger equation. And the CSE, it turns out, depends not just on the 2-RDM, but also on the 3 and 4 electron reduced density matrices. However, a really fascinating result, though, is if these reduced density matrices are kept n-representable, meaning that they represent some n-electron quantum system, then there's a one-to-one mapping, okay, between the CSE being satisfied and the Schrödinger equation being satisfied. So we can actually satisfy the contracted Schrödinger equation, and that implies a solution to the Schrödinger equation. Okay, this important relationship was first discovered by Hiroshi Nakasuji in his 1976 paper published in Physical Review. Now, we could consider a particular part of the contracted Schrödinger equation. So for example, if we just think about the anti-Hermitian part of the CSE, then our equation actually ends up introducing a commutator, and we have the equation on the right. It's not quite as general as the CSE, but it's still pretty close to the CSE. And now it depends only on the 3-electron reduced density matrix, which is one of the key advantages for the anti-Hermitian contracted Schrödinger equation. And we'll see another advantage in just a moment here as well. So there's an important link between the anti-Hermitian part of the contracted Schrödinger equation and unitary transformations. So if we consider an infinitesimal expansion around the wave function with respect to an anti-Hermitian two-body operator A sub n, then we can write an iterative algorithm for updating the wave function in the following fashion. We take our wave function at iteration n, and we apply this exponential of this two-body anti-Hermitian transformation. So it's a two-body exponential transformation that's unitary. And this unitary transformation will now take us to the new wave function at n plus 1. But importantly, if we now differentiate the energy created by this transformation at the n plus 1th iteration with respect to the elements of the two-body anti-Hermitian transformation, then the derivative of the energy with respect to these elements produces the residual of the ACSE. So basically, the residual of the ACSE is the natural gradient with respect to the elements of this unitary transformation. And so we have an important link then between zeroing, essentially, or finding the minimum, variational minimum with respect to this Onsots for the wave function, and essentially finding the minimum, the zero, the residual of the anti-Hermitian contracted Schrödinger equation. And this is important because basically it shows that by trying to satisfy the ACSE, so if we iterate this algorithm, the gradient will vanish, okay, if and only if the ACSE's residual vanishes. And so we can use insight into, and this basically insight from these anti-Hermitian contracted Schrödinger equation, the desire to solve this equation to actually construct a systematic Onsots for generating the wave function on a quantum computer. Okay, so before we get to quantum computing, we can perform a solution to the ACSE on the classical computer, and this was developed over a decade ago by research in our group and other groups. And the basic idea is that one needs, though, a way of removing the indeterminacy of the ACSE. It's indeterminate because the equation depends not just on the two-electron reduced density matrix, but also on the three-electron reduced density matrix. So one approach is to try to reconstruct the 3-RDM from the 2-RDM by a cumulant expansion. And so here we have D3 is equal to D1 wedge with D1 wedge with D1, which is equivalent to a mean field part of the calculation, plus a coefficient times delta 2, which is the cumulant or connected part of the 2-electron reduced density matrix, wedged, okay, with the Grassmann wedge product with D1, plus a delta 3 part, which is the cumulant 3-RDM, or the part that cannot be written as wedge products involving lower reduced density matrices. So we can approximate this cumulant expansion for the 3-RDM from the 2-RDM, and in the process make the solution of the ACSE on the classical computer solvable. Here's an example of a calculation just to show what can be done. So for example, if we look at a photoexcited conversion of gauche 1,3-butadiene to bicyclobutane, we have a photoexcitation. We go up into the gauche butadiene star, and then a rearrangement of geometry occurs, taking us to a conical intersection. And interestingly, the conical intersection, which we were able to identify for the first time, lies very close to the disrotatory transition state. So you can see the geometries are essentially the same, at least by the eye, and energetically a little bit different. So relaxes a little bit more here. And once you get to the disrotatory transition state of the ground state, okay, relaxing from the excited state through the conical intersection, now essentially one can take this pathway down to the lower energy structure, the bicyclobutane. Okay, so basically we're able to use the solution of the ACSE to map out this potential energy surface. And it's non-trivial because the conical intersection and the disrotatory transition state are strongly correlated. And so a method, for example, like coupled cluster would not be able to really predict the conical intersection in this particular system. We can also take a quick look at singlet triplet gaps, and here's a variety of different methods. And you can see the ACSE does as well as any of these methods in terms of getting mean signed error or mean averaged error relative to other techniques. And again, these are a variety of different Monte Carlo methods, as well as complete active space, self-consistent field methods, etc. Okay, so getting back to solving things on the quantum computer, we want to think about this notion of contracted quantum eigensolvers, or CQE. So the idea now is the contracted quantum eigensolvers are basically, it's an algorithm that's going to minimize the residual of the ACSE to find the ground or excited energy and 2-RDM of the molecule. Okay, so how does that exactly work? Okay, so here's the algorithm. It looks a bit complicated, but it basically has just a couple of key parts. So first, up here in the left corner, we basically initialize the 2-electron reduced density matrix and the initial wave function. And then we use that to obtain the residual of the ACSE. Okay, so that residual is calculated on the quantum computer, or it could actually be calculated classically if we have a reconstruction for the 3-RDM or a measurement of the 3-RDM. But we can actually just directly do it by creating essentially an extra state on the quantum computer, this gamma state. And this extra state on the quantum computer can be used then to directly compute the residual A2 of the CSE. We can look at the residual to see if it's small enough. If it's small enough, we can just stop. If it's not small enough, then we proceed to use the residual to update the wave function through a unitary transformation to construct the new wave function. And then we can go ahead, tomography the 2-RDM to bring that back over to the classical computer, trace that against the electron integrals, and obtain the energy and see, okay, now what's the new energy? And then we basically repeat this process until the residual of the ACSE is small enough, and we've solved the ACSE with our quantum algorithm. And our experience is that actually solving the ACSE basically implies a solution, a practical solution to the Schrödinger equation. So we're not just getting a minimum that corresponds to an approximate Onsots for the wave function, but rather we're using an Onsots that's sufficiently flexible to basically reach the exact full configuration interaction solution on the quantum computer, at least in the absence of noise. So there are really two key parts here in the algorithm. So first of all, what are some of the advantages? The CQE does not require reconstruction of the higher reduced density matrices. So this is the key advantage relative to the classical algorithms, and it implies a potential exponential advantage for performing a solution of the ACSE on the quantum computer. So the reconstruction is replaced by two different processes: one, state preparation on the quantum computer, and tomography. So we're basically preparing two different states on the quantum computer. The first one is the update of the wave function using the residual of the ACSE. And that basically then is measured to get a two-electron reduced density matrix from that state. And then we prepare another state, which is related to taking the wave function at the nth iteration and applying essentially an exponential of plus and minus I delta H. And we use basically the plus and minus to create two different gamma states, plus and minus. And the important thing is from these two gamma states, which are have the same, they're actually the same shape and size as the two RDM, we can take the difference between them, which is essentially a finite difference divided by the finite difference step size, and obviously a 2 because it's a centered finite difference. And then we basically end up with a numerical approximation to our residual of the ACSE, but without actually reconstructing the higher reduced density matrices. And of course, this approximation is accurate to the order of del square. So there's a little bit of error in computing the gradient, but we find in practice that error is not important. Okay, so we basically can perform these two-state preparations on the quantum computer, perform a series of measurements, and then use that to construct essentially a search direction to improve our wave function iteratively on the quantum computer. How does this compare, for example, to other algorithms in the VQE, for example, Variational Quantum Eigensolver framework? So first of all, probably some of the fastest algorithms are to sort of use the VQE with a unitary couple cluster singles doubles Onsots. So the CQE is really more of an accurate calculation because our Onsots basically goes significantly beyond a couple cluster singles doubles Onsots. Even though we're essentially using a series of two-body unitary transformations, it's known in the ACSE literature, in the contracted Schrödinger literature, that this Onsots essentially is exact, even though we don't need to use higher, triple and higher excitations of the couple cluster. And then over here, in this other area of the Venn diagram, we can have sort of what are in principle cheap methods in the noisy intermediate scale quantum error. And so these are basically hardware encoded or hardware efficient variational quantum eigensolvers, where we essentially just try to apply kind of a bunch of different unitary transformations that are easy to generate on the quantum computer. And we vary some parameters in that and try to, get that to come down. For example, the Nature paper from 2017 is a good example. The Kandala paper is a good example of that type of method. So it's inexpensive, but basically maybe not so accurate. And maybe not so fast because, again, as one is doing that, one can unfortunately get caught in local minima and sort of barren plateaus in the optimization because the Onsots itself is not really tuned to improving the result at each step. So the CQE tries to balance some of the limitations of the fast category and the cheap category to come up really with a highly accurate method. Okay, so the variational quantum eigensolver doesn't really have an intrinsic Onsots. It can generate Onsots. Of course, you could use, for example, like a couple cluster singles doubles, a unitary couple cluster singles doubles Onsots. But again, that's an approximation to the full CI. The CQE has a built-in intrinsic Onsots. And importantly, the ACSE Onsots provides convergence to the full configuration interaction result. Now, we can also compare this to the AdaptVQE algorithm. And in the AdaptVQE, it shares some of the properties of the CQE algorithm. So it is iterative, and it also uses an ACSE like Onsots. So it actually borrows the Onsots or uses an Onsot similar to that in the ACSE literature. The main difference, however, is that in the AdaptVQE, it's still a VQE algorithm. It's still a variational quantum eigensolver. And so basically, like the Rayleigh-Ritz variational principle, all parameters are repeatedly reoptimized in the AdaptVQE algorithm. So even though one's iteratively adding exponential unitary transformations from a pool of operators, at each step, the parameters in all of these operators are being optimized over and over again. Whereas in the CQE, we recognize that we can essentially apply a series of unitary updates, but we only optimize or re-optimize the parameters associated with the latest update. Okay, and so it's, in that sense, more of a kind of a greedy algorithm where at each step, we're basically getting the most out of that particular iteration. And so the parameters of the current iteration are optimized. So there are important connections, but there are some differences in terms of how the CQE is designed. Okay, so let's look at an application of the CQE on a quantum computer to get a sense of how it works. And so one application that we've looked at is to the correlated isomers of benzyne. And benzyne's nice because it has 3 different isomers. It's got the ortho, meta, and para isomers, where we pluck off 2 hydrogens from benzene in different positions on the ring. If we pluck them off, obviously ortho, meta, or para, you can see here going from left to right, the degree of correlation increases as you go from ortho to meta to para. When the 2 radicals are close to each other, it's essentially not very strongly correlated. Whereas in the para case, when the 2 radical centers are separated at a greater distance, we see the emergence of fractional occupations here on the right. Okay, so to treat this technique, or to treat this molecule, the benzyne isomers, we had to introduce some additional error mitigation methods, because quantum computers, of course, in the NISQ era are very noisy, and we need ways of ameliorating or mitigating that noise. So there are 2 different error mitigation methods that we developed in the context of this work. One's called a limit-preserving correction. It's a fairly simple correction, but it turns out to be useful. And the other one is to use n-representability conditions, or an n-representability correction. Okay, so let's talk about both of them, and then we'll focus a little bit more on the second one. So the idea of limit-preserving correction is the following. We're applying essentially a unitary transformation to update the wave function as we go from the nth iteration to the n+1th wave function. And we can think about kind of a thought experiment. Well, what happens on the quantum computer in the limit that our epsilon parameter goes to 0? Well, then essentially our exponential of epsilon times the A operator is really just going to be e to the 0, which is just the identity matrix. And so we shouldn't go anywhere. We should just go from our wave function at iteration n to the same wave function at psi n+1 will be the same. It won't go anywhere. However, on a quantum computer, because of the noise, in the limit that epsilon gets small, there can actually be a bit of a shift that occurs from the noise on the quantum computer. And so the limit-preserving correction recognizes this shift can occur. It looks to see what happens to that shift as a function of epsilon getting small, and then performs essentially a reverse of that shift to undo the error on the quantum computer, at least in a linear sense. Okay, and so that's the basic idea, and here's sort of the math kind of associated with that. We end up accumulating sort of shifts over the number of iterations, and so those shifts, at least in a simple approximation, become additive to shift it. Importantly, because the algorithm is iterative, at each iteration, it can basically adjust for the fact that error occurred from noise in the previous iterations. And so in that sense, there's also an advantage to the iterative nature of the CQE algorithm. Now, our second error mitigation technique is to invoke n-representability conditions. So what exactly are these n-representability conditions that we're talking about? Well, when we generate the 2-electron reduced density matrix by tomography, in principle, if we have a noise-free or fault-tolerant quantum computer, then we're going to get the exact 2-RDM out. All the operations are completely physical. They're all unitary transformations. So the 2-electron reduced density matrix would exactly correspond to a contraction of an n-electron density matrix. However, because the quantum computer is very noisy, the 2-RDM that we measure at the end, from a variety of different reasons that affect both the state preparation and the tomography on the quantum computer, cause the 2-RDM to basically fail to really represent the N-electron quantum system. And so what we can do is we can correct that or mitigate those errors by thinking about the fact that we know some of the constraints that exist on the 2-RDM to ensure that it actually represents an N-electron quantum density matrix. And these are called N-representability conditions. Some of the simplest ones are called the two-positivity conditions. And here you can see, so basically they take the form of taking different metric matrices for the 2-RDM. So one metric matrix, D2, is called the particle density matrix, reduced density matrix. And you can see that it comes from the expectation value of A dagger, AA, so two creation and two annihilation operators. We can also look at the whole version of this, the two-hole reduced density matrix. And essentially that comes from looking at the expectation value of AA, A dagger, where we now essentially create two particles and then kill them. Or basically the G2 matrix, which is the particle hole reduced density matrix, where we kill an electron and create an electron. And so we're looking at the probability distribution for a particle hole or an exciton in the system. So it turns out each of these metric matrices contains the same kind of information in the sense that we have a linear mapping from D2 to Q2 to G2. However, these linear mappings produce matrices that may or may not, okay, the positive semi-definiteness of one matrix does not imply the positive semi-definiteness of another matrix. And so on the left here, you can see the constraints called the two positivity conditions are to basically keep both the particle-particle, the whole, and the particle-hole reduced density matrices positive semi-definite. And of course, to be positive semi-definite, these matrices, must have non-negative eigenvalues. Okay, so that's the idea. And so what we're going to do is we need some way of taking the 2-RDM that comes from the quantum computer and projecting it onto the N-representable set. Okay, and so we do that by a form of optimization. We're going to use something called semi-definite programming. And so semi-definite programming is a generalization of linear programming, where instead of just having linear basically inequalities as constraints on our program, we generalize that to allow linear matrix inequalities or semi-definite constraints, matrix inequalities, positive semi-definite constraints. What we're going to do is we're going to minimize a function f such that this error, okay, an E matrix is defined as the D2 that we measure on the quantum computer minus the D2 that's going to emerge from solving the semi-definite program. We want to make that difference between that distance between these two matrices as small as possible. So we create a slack matrix of the following form with an identity matrix in the upper left corner, and then the F matrix, our free matrix, in the lower right corner. And then we have these basically these distance matrices on the off-diagonal elements of our 2x2 block matrix. And we're going to keep this matrix positive semi-definite. And you can see that if we minimize the trace of F, then because this matrix is positive semi-definite, that's going to provide a relaxation to minimize the error or the distance between D2 and the D2 from the semi-definite program. And then in addition to that, we add the restriction that this D2 must map to Q2 and G2, and that this entire matrix must also be positive semi-definite. And so if we solve the semi-definite program, we end up projecting ourselves onto the two positive set of reduced density matrices, and we obtain the 2-RDM that satisfies the DQ and G conditions, but is closest in a least squares sense and in basically a Frobenius norm sense to the 2-RDM measured on the quantum computer. Okay, so this basically gives us a form of what we call correlated purification, where we take the 2-RDM and we sort of purify it to follow conditions that would be necessary for it to be represented by a pure state and particle wave function. Again, just necessary conditions, but important conditions for that to be true. We call it correlated purification to distinguish it from the traditional purification, for example, McLeany purification, which is used to guarantee idempotency for non-interacting matrices. Okay, so how does the actual whole process work? Okay, so we basically perform the error mitigation. we do some standard error mitigation, then we do the limit preserving corrections, and then ultimately we perform this purification to put on the adaptability conditions. So how does that actually work when we put it all together? So here are the relative energies of the isomers that we're aiming to calculate. We can see on the right here, the Hartree-Fock does not predict the relative energies correctly because, again, the relative energies are going to be significantly correlated, especially para isomer of benzyne. So we need to have electron correlation. If we use a 2-2 CAS active space, 2 electrons and 2 orbital complete active space self-consistent field calculation, then we end up with these splittings between the ortho. The para is the highest, then the meta, and then the lowest is the ortho. We can do the same 2-2 active space using a quantum computer with 1 qubit, and you can see we reproduce the results quite accurately. So basically, because a 1 qubit calculation can be the error can be mitigated tremendously well on a quantum computer. Now, if we go to a larger 4-4 active space, then the energy difference on the classical computer looks like this. If we do that on the quantum computer, using 3 qubits to approximate that active space, we have these gaps here. If we use no approximation in terms of qubits, but the 4 qubit case, then we end up with these differences here. Interestingly, you can see that as we use more qubits on the quantum computer, even though the results should get better in a theoretical sense, because if we had an exact quantum computer, the noise essentially makes things a little bit worse. But again, we end up with good results in all of these cases relative to the classical results. Okay, so we're basically within 1.6 kilocalories per mole of the ideal results. And so it's important the ACSE is really giving us an Onsots that's extremely general and is able to capture kind of full CI-like behavior that's going to be important for a complete active space self-consistent field calculation. Now, in the remaining time, I want to talk about kind of briefly 2 areas of further advance that we've actually just kind of recently submitted. In fact, I think it just showed up on the archive this morning. One is called the unencoded contracted quantum eigensolver. So molecular simulations are obviously, we're dealing with electrons, which are fermions, and so our wave function has to be fermionic, meaning that we need to have the fermionic character. If we switch to electrons, we need a change in the sign of the wave function, from the Grassmann algebra. However, basically qubits, of course, are not really fermions, and so when we prepare excitations on the quantum computer, we have to sort of build in the character by a product of basically, we have to have a whole bunch of products of Pauli Z gates to count essentially how many particles in a certain order and then get the appropriate sign changes from that. Okay, and this is called the Jordan-Wigner transformation. And so one has to do this encoding of the wave function into qubits, where B dagger is the qubit operator representing the qubit excitation, and A dagger is the fermionic excitation operator. Now, there's something called hardware efficient Onsots, where we encode the fermions in a qubit Hamiltonian, and then we use any qubit wave function built from the gates. So the idea is to try to just convert the fermionic problem into a qubit Hamiltonian, and then just build your wave function from different qubit gates. However, as I mentioned earlier, that can lead to optimization issues and barren plateaus, partly because the Onsots can basically have a lot of trouble finding an improving direction. And of course, we know that from optimization theory that you need to have good search directions to really go towards the solution. Now, we can improve the situation by thinking about something called qubit particle wave functions. So the idea is to use qubits, but to retain the concept of particles and excitations. So we use the qubits in a more restricted fashion. And we find that this has better agreement with fermionic encoding. So a series of papers have recently emerged looking at this, work by Sabre-Kais, by Barnes and Yordanov, as well as Ismailov, have all looked at some form of qubit particle wave functions with different degrees of restricting the qubits towards a particle-like picture. And so we were thinking about, okay, why does this work? What is the key aspect of this? And we realized that in a recent paper that we published in NJP, that basically there's an isomorphism between the fermionic wave functions and qubit particle wave functions. And so we defined this notion of qubit particle wave functions as essentially the fermionic wave functions is just a linear combination of Slater determinants. But now the qubit particle wave functions are just a linear combination, not of Slater determinants, but rather permanents, where the orbitals are, instead of anti-symmetrized, the orbitals are symmetrized. But otherwise, everything is identical. And therefore, this expansion coefficient here has the same degree of complexity as the fermionic expansion coefficients here. And that essentially proves that we have kind of an isomorphism or a bijective mapping between these two sets of wave functions. And that's important because what it shows is that mathematically, we really have the same flexibility in the qubit particle wave functions that we have in the fermionic wave functions. And importantly, we don't have more flexibility, which could lead to optimization problems. And it turns out then one can prove that the two-electron reduced density matrix is a functional, the unrepresentable one, is a functional of both the fermionic wave function or wave function set as well as the qubit particle wave function. So we can, in principle, get the exact fermionic 2-RDM as a functional of the qubit particle wave functions in a way that has a one-to-one mapping. Okay, it has an isomorphic or a bijective mapping. Okay, so how do we set up this qubit particle Onsots? We prepare qubit particle wave functions on the quantum computer, and then we use no fermionic encoding in the preparation in the preparation stage. But then we encode the fermions when we measure the 2-RDM. Okay, and so this idea is applicable to both the VQE and the CQE algorithms. And again, we basically have it so that we know that we can get the exact 2-RDM from using these qubit particle wave functions because of the isomorphism that we have with the fermionic case. So we recently applied this in this archive paper to create something called the unencoded contracted quantum eigensolver. And the basic idea is to solve something called the unencoded ACSE. So the unencoded ACSE is taking the Schrödinger equation and now projecting it onto the qubit particle space, B dagger, B dagger, BB, instead of A dagger, A dagger, AA. And we're going to go ahead and we're going to optimize this unencoded ACSE to send it to 0. And that's going to imply that psi is at a minimum with respect to two-body qubit particle excitations. So now the question is, how does the unencoded approximation affect efficiency? How does it affect accuracy? Well, in examples with 28 qubits, there we would have greater than 200,000 or 200 million states. There are 92,000 elements in the fermionic 2-RDM, but only 6,000 encoded 2-RDM circuits for the fermionic 2-RDM, but only 92 encoded 2-RDM circuits. So you can see that we have a significant reduction in the tomography required and the preparation required for basically using qubit particle wave functions. Now, how does it do in terms of accuracy? Well, it turns out computational experience shows, and some theoretical analysis indicates, that we can get the same accuracy with fermionic or these encoded or unencoded CQE. So the A here represents the circles, represent the error, or represent the points on this potential energy surface of pulling apart the H4 chain. The circles represent the fermionic case, and the X's represent the qubit particle case. And here we're on a log scale, so you can see that the error across the potential energy surface is really the same for both fermions or both the fermionic encoded one or the unencoded qubit particle version of the contracted quantum eigensolver. And yeah, so basically we're getting accurate results throughout, and you end up with the same potential energy surface in either case. Likewise, we can dissociate the O2 molecule, and as we dissociate the O2 molecule, you can see that we end up with accurate results across the potential energy surface as well. Okay, so essentially the same energies for differing degrees of correlation. We can get the correlation both at equilibrium as well as at the non-equilibrium regions, and it really doesn't matter whether we use the encoding or the unencoding, but using the unencoded wave functions can, in principle, provide significant computational speedups. Finally, I want to just finish the discussion with a comparison here that we recently put on the archive as well. I think the archive label ended up over here instead of over here, but we compared VQE with ADAPT and our CQE algorithms here for the H6 chain, and at a distance of 1 angstrom on the left and a distance of 2 angstroms on the right. Here we have the log of the error relative to full CI. You can see that the CQE, which is the diamonds here, shows very rapid convergence to the result. The VQE also shows rapid convergence here. You can see, though, when it becomes strongly correlated, the convergence levels off because we're using a couple cluster singles doubles Onsots. Whereas because the ACSE Onsots is much more flexible and can go to the full CI result, you can see that the CQE comes down and continues to go down, giving us superlinear convergence. In this particular case, we're using sort of a recent advance where we implemented a quasi-Newton second order optimization scheme to accelerate the convergence. And you can compare that to the performance of the ADAPT. The ADAPT basically takes a lot more iterations. It also gives very good accuracy, but it takes more iterations as it has to basically perform the optimization of essentially the inner parts, as well as at different iterations as performing optimizations of the variational parameters in the framework of a VQE algorithm. Okay, finally, I just want to acknowledge, in particular, two of the students who did a lot of the work here. So especially Scott Smart, who's standing over here on the right in the University of Chicago sweatshirt. Scott, just did tremendous work on the quantum algorithm developing the CQE, and he basically really did the calculations throughout the talk that I presented today. I also want to highlight standing kind of right next to me over here by the Henry Moore statue at the UChicago campus is Nick Boyne in the red jacket. And Nick was instrumental in doing the benzyne work and also connecting our quantum algorithm with some classical algorithms to look at how the error on the quantum computer would affect a recovery of the total electron correlation energy. And finally, I want to just again thank the organizers for the invitation and thank the audience for your attention today. And if there are any questions, I'm definitely happy to answer any of those now. So, all right, thank you so much.